of arithmetic coding. Example of arithmetic coding. Let xi be Bernoulli P, and I'm going to turn x1, x2, etc., which might be, say, 0, 1, 1, 1, etc. And I want to calculate what f of x is. And this is u, which is going to turn out to be this Bernoulli a half sequence. So how do I map a Bernoulli P into Bernoulli a half? Well, f of x is the probability that this x, this infinite sequence x, so x is equal to this, point that, point that. How do I, what's the probability of this? Well, the probability, say that x, let's say, let x equal 0, 1, 1, 1, etc. This is the example. Probability x is less than 0.0, 1, 1, 1, etc. I don't know how it finishes. Could be zeros and ones. There'll be roughly NP ones and NQ zeros in a batch of length n. Okay, so let's look at the process. 1, 0, 1, 0, 1, 0, etc. What's the probability that this Bernoulli P process falls lower in the tree than this? Because that's what the numerical ordering with the decimal point does. It orders things alphabetically or numerically. Well, this turns out to be the probability that it's 0, 0 for the first two terms. That is, if x is going to be less than this, there better be 0 in the first term, otherwise it'll be greater. And it can first deviate here, 1 giving 0, 0, plus p 0, 0, 0 for this, 0, 1, 0. That is, it agrees, the Bernoulli P process agrees the first two terms, first deviating in the third and being less than, plus p of 0, 1, 1, 0, plus, etc., however it finishes. So for this sketch, here's the 0, 0 sequence. Here's the 0, 1, 0 sequence. And here's the 0, 1, 1, 0 sequence. So remember, this sequence is what's happening. And these are all the sequences that are less than that in the numerical order. And what we're trying to find is f of x, the CDF. So we add up this probability, this one. And every time we fall off this, we add them up. Notice there are an infinite number of sequences that are less than 0, 1, but we can sum them all up by just saying the first two terms are 0, 0. That's what makes this easy to calculate. Otherwise, you'd have to put probability masses in all the infinite sequences and add them up. But you can do it sort of sequentially, on the fly. And that's good. By the way, for this, it turns out to be, x was Bernoulli p, so this is q squared plus PQP, QPQ plus QP squared Q, etc. Great. Now let's see what the CDF looks like. The CDF looks like this for, well, if we break it off at block length 3, in any case, it looks like this. This is f of x, or this is u, equals f of x, and here's x, drawn according to whatever distribution f it is. And U is uniform. Okay, now, let's decode this. All right, we take this interval, 0, 1. The term starting with a 0, there's Q of and P. If x starts with a 0, it corresponds to f of x being below q, and so on. In any case, we keep dividing this. This is now pq. This is of length q squared. This is pq. And this is p squared. Okay? Now the nice thing is this. As you get more and more bits of u, you know more and more about which interval x has to fall in. X, remember now, is this infinite sequence with a decimal point in front that we turned it into a real number, so the ordering is obvious. And in fact, after a while, suppose we're given U1, U2 through UK here, and the jumps at time n, this height will be P of x super n. I said, wait a minute, f of x has no jumps, and all of a sudden it has jumps. Yes, if we cut it off at finite block length, it'll have jumps. But as we let x go, the sequence go unfold, we keep refining this until we get a distribution function with no jumps. So if xn is here, and it maps into this quantile, saying essentially the total probability of all the random sequences of length n that are lower than this in the numerical or lexicographic order is this. And I know this to accuracy half to the k, so I get half to the k. As soon as this is equal to the jump p of xn, I will know what xn is. That's roughly true. There are some p's that straddle these things, but most of them are strictly contained, especially if p is less than half to the k, strictly contained in an interval. And so if I know k bits of u, I now know xn precisely. Now what? Well, that's k equals log 1 over p of xn. So the number of bits of u I need to know x to n-bit accuracy is log 1 over p. And the expected value of k is summation p of xn